Alrighty. So how do I make this big screen? Can I? Let's see if I can make it full screen. I don't know. Oh, there it is. There we go. Alrighty. Go for it.
Alright. So as most of you know, my name is NaomiHayes, and today I'll be presenting on the blue crab. And I'm sorry that my conference in Zimbabwe has kept me from presenting in class, but through the Skype, I should be able to probably do it. Alright. So, just as an overview, I'm first going to talk about blue crabs as a species and why they're important to neurophysiology. We go on to more specifically the proprioceptor, or also known as chordotonal organs, and then the purpose of our experiment, the methods, the results, and then finally the conclusion. I can hear my voice echoing in the room. But, alright, so blue crabs are also known as Calanicus sapidus, and the reason why they are a good research subject is, first of all, they're native to the eastern Atlantic coast, easy to get, and first of all, also cheap. They're also very common in your Maryland crab bakes. But another reason is the receptor cells are very large and easy to expose through dissection, and they have long-lasting nerve readings. So even if you prepare a species and keep it on ice, then you can do an experiment on it for a very long period of time. And you don't have to worry about it dying necessarily. Okay. To go into a little bit about the proprioceptor cells, crabs and also other types of crustaceans have multiple joints in their limbs, and for our experiment, we were specifically looking at the crab leg. So chordotonal organs are used to sense joint movement and also static position. So they are the ones in charge of basically, I guess you could say, measuring how just the movement of the crabs and how they should move. And the crabs have 6 joints, and each of them has a different proprioceptor organ. And if you look at the diagram at the bottom, which is about right here, it kind of lists the different types of proprioceptor organs in the crab leg. And the way these proprioceptor organs function is the joint receptors consist of an elastic band inserted into the dendrites. So there's an elastic band basically connected to the end of the neural cells where they can receive the signals and bend, and then in turn bend the leg or limb. So the purpose of this experiment is basically to record neural activity from the joint movement. And with this experiment, we tested for 2 different variables. We tested the difference between the angle and also the speed of how fast you bent it, and see how much of a change in the reaction was. And then part 2 was we also did stain the neurocell, stain the crab leg so we can see the neurocell bodies close up using methylene blues dye. So the methods. Well, Dr. Cooper was kind enough to dissect our crab legs for us, but here we have an open crab leg, and if you see this little cord right here, that is the nerve we sucked up. That would also be the tension elastic nerve. And up here is where the nerve bundle was, and we cut it approximately at the base of there. And of course, we sucked up quite a bit of it so it wouldn't come out when it was moving. But this is kind of a closer up diagram of it. The nerve would be here, and then this is the main leg there. And then as each and every one of us have used this setup, we used the usual Faraday cage and the dissection microscope through the sucker with our power lab and amplifier and then lab chart. So with that, we were able to record our electrical responses. Alright, getting into the results. For the first trial, we simply measured it at the angle. 90 degrees is, by 90 degrees we mean that the arm was fully extended towards the body. So if you can see me in that little window, like this is my crab leg. Towards the body would be 90 degrees. And then 0 degrees is what I just went through. I used 0 degrees because that's what they use in the protocol compared to like 180 degrees because we're having some trouble, I guess, finding a basic measurement, but it's where you take an interest out. So if you see from the results here, 90 degrees when it's pulled in, we got fairly consistent response. But if you see the 0 degrees, we had a much a taller peak in our responses. To continue on, we have a similar test, but here we were measuring time. And from this trial, we went from 90 degrees, which means pulled in towards the body, and then out to 0 degrees, which is fully extended. So basically, this would simulate the action of the crab extending its leg during movement. And you see from the first trial, this is 90 to 0 in 1 second. And we get a pretty, a good burst of reaction, and then after a while it would slow down. If you do it in 2 seconds, you get a more sustained reaction. And I think I'm going to close this window so if it stops, I'm sorry. But this is similar to the last one, but it is reversed. So if you notice, it's from fully extended to inward. So it's basically the arm retracting back towards the lung. So in 1 second, you get, like in the trial before, you have less, sustained reactions. If you see here from the 2 second, you get more prolonged neural responses. And this is when we held the leg out for extended periods of time at certain degrees. So if I held at 0 degrees, that's when we kept it out fully extended and held it for a couple of seconds without moving it back. And this is the same for 90 degrees. And once again, when it was fully extended, we got higher peaks than, say, the 90 degrees. And as for the results for the staining, you see right here, this is where the nerve bundle is, and from a picture graciously taken by Joss and emailed to the class, you can see a close-up of the nerve cell bodies stained in blue. And these are the nerve cell bodies that will be then connected to the main tension elastic nerve, which will be controlling how the muscles contract in the crab leg. So in conclusion, there was more rapid firing when the crab leg was extended as compared to pulled inwards, 90 degrees. So there was more of a response at 0 degrees compared to 90. And there's also a more sustained response when the leg gets extended for a long period of time. And into further the field of science, I also realized that blue crabs can become a great Thursday night meal. And that is the end of my presentation for now, but if anyone has questions, feel free to ask.
How did you cook the crab?
Sorry?
How did you cook the crab?
Well, the crab initially was alive. I did sadly lose 2 of the crabs on the way to my house. I think those are probably the ones previously experimented on, so they're probably a bit tired. But basically, you heat a pot of water, you boil them, you'll take them out, and then I looked on the internet, you'll open them up, take out the gills. After that, I created a nice miso chili paste sauce that tasted really good, and yeah, basically that was it. Okay. Come on back.
Fun thing. Let's see if I can. Whoops. I'm happy here. Let's see if the echo's still going on. I think it is.